In this video, we're covering complex numbers. Thus far, you have only dealt with real numbers in the number system. You will now begin to work with complex numbers. To understand complex numbers, we must first understand what imaginary numbers are. Now, imaginary numbers, together with the real numbers, are the building blocks. They can be thought of as the building blocks of complex numbers. Now, it may seem a bit confusing, so let's take a look at this diagram below. All right, here is the number system. Now what I'm circling in blue, these are the real numbers. These are numbers that you have been working with and you know them fairly well. So on top you have the real numbers, and the real numbers are divided into rational and irrational. Under rational we have integers, then we get whole numbers and natural numbers. So that's nothing new. You've been working with real numbers, like I said. Now what I'm going to do is I'm going to introduce you to imaginary numbers, right? So we're going to consider what they are. Then real numbers and the imaginary numbers, when we consider them together, give us complex numbers. That's why the real numbers and the imaginary numbers are basically the building blocks of complex numbers. Now I just want you to take a look at these letters that I have in here. So we are going to consider a real number A, and we'll get an imaginary number, and we can represent imaginary numbers as b times I. Don't worry about what those are right now. I'll explain it when I'm covering imaginary numbers. So when we combine a real number plus an imaginary number, we get a complex number, hence why I have a plus bi. But again, I'll explain what that means in detail. So let's look at what imaginary numbers are. Now, the imaginary unit is the basis of imaginary numbers. So you have all imaginary numbers, and at its core, the building block of imaginary numbers is the imaginary unit. Now, the imaginary unit is denoted by I and has the property that I squared is equal to minus 1. Now, at first glance, this doesn't seem like a big deal, right? I squared is equal to minus 1. So we have I squared is equal to minus 1. This gives us, so what I want you to do is square root both sides, right? So we have I squared, we have the square root of I squared here. What we are going to get is just I is equal to the square root of minus 1. And that's when it hits. How can we get the square root of minus 1? How do we get the square root of a negative number? Previously, when we were only discussing real numbers, we said that we can't get the square root of a negative number. Now all of a sudden we can. And that's because we are dealing with imaginary numbers. This is imaginary, the imaginary unit. So I, the imaginary unit, is equal to the square root of minus 1. But more formally, it's defined as I squared is equal to minus 1. That's its property. So we're going to work with this imaginary unit and see how we can use it. Now, when simplifying expressions involving the imaginary unit, it is useful to obtain terms involving I squared, because remember, I squared can be simplified to minus 1. And sometimes in some situations, it may also be helpful to treat I as a variable. Okay, so we can treat this as if it's a variable, because after all, it is technically a letter, so we can treat it like any variable that we have, like x, y, whatever the case is, depending on the situation that we are in. I find it helpful to treat it as a variable sometimes. But again, we'll go through some examples. All right, example 1. So these are super simple. All I want you to do is simplify the following expressions. Okay, let's do this. So let's go for A. We have minus I cubed. Now what we want to do when we simplify is get terms involving I squared, because we know that I squared becomes minus 1. So this is going to be equal to minus. Let's open a bracket because it can be a bit tricky if you're doing this for the first time. Now we have I cubed, and I cubed we can write as I squared multiplied by I. So this is minus into bracket. I squared we know is minus 1. That's its property of the imaginary unit. So it's going to be minus 1 multiplied by I. So it's minus times minus 1, that's going to be positive, and we just have I. So there's your answer. Minus I cubed is just equal to I. All right, let's do question B. Okay, so for question B, we have I to the power 7 minus 6I. So it's the same situation. We want to get terms involving I squared. So this is equal to, now I to the 7, that is I to the 6 multiplied by I to the power 1. Okay, but we don't have to write that power 1 because we know it's there. Okay, I to the 6 multiplied by I, that gives us I to the 7. The minus 6I we are going to leave as is. We can't really simplify this any further, so we are going to leave it as is. Now I to the 6, we can write that as I squared to the power 3. So it's I squared, then cubed. Using the law of exponents, this will become 2 times 3, that's 6. That's why we have I to the 6. And then it's going to be multiplied by I minus 6I. Now again, I squared, that's equal to minus 1. So it's minus 1 cubed, that is going to be minus 1. So we have minus 1 multiplied by I, well that's just negative I. So we have negative I minus 6I, that is going to be minus 7I. So I to the 7 minus 6I is equal to minus 7I. That's how we simplify uh, expressions involving the imaginary unit. This was question B. Exercise 2. So it's the same situation, you just need to simplify this expression. All right, so 9I, we cannot simplify that any further. We'll just leave that as is. Now we have minus, and we have minus I squared. Now be extremely careful with this. What I suggest you do if you're doing this for the first time is say minus in brackets I squared, because the double negative sometimes can catch you out. Okay, so it's going to be minus in brackets I squared. Now I squared, we know that is minus 1. So if you just said I squared is minus 1, you may have erroneously wrote 9I just minus 1. You would not have accounted for the double negative, so don't make that mistake. So it's 9I minus minus 1, and then we have plus I cubed. Okay, but we know that I cubed is going to be I squared multiplied by I. And I squared, that is minus 1. So let's put that in brackets. So it's going to be 9I minus minus 1, that's plus 1. And then we have minus 1 times I, that's minus I. There we go. So it's going to be 9I minus that. We are going to have 8I plus 1. Or what we write conventionally is we write the real number first. So it's 1 plus, and then the imaginary portion. But I'll explain how that works in the next slide. So it's 1 plus 8I, that's your answer. So let's look at complex numbers. And complex numbers, apart from their name, aren't really that complex. They're super easy to work with once you get the hang of them. So complex numbers are basically a combination of real numbers and imaginary numbers, as I said on the previous slide. Now a complex number has this form. So it's a plus b times the imaginary unit I, where this a and the b are both real numbers. The only thing here is that that b, which is a real number, is being multiplied by the imaginary unit I. So this has two parts. So this is the complex number. It's a plus bi, and it has two parts. A is the real part of the complex number. So this a is one part of the complex number. And the b times by I is the imaginary part of the complex number. So it's b times by I, that's the imaginary part. So here's real, here's imaginary. And let's just take a look at the previous example again. In this example, our answer was a complex number. Why? The 1 is the real portion, and the 8 times I, that is the imaginary portion. So this is a complex number. Let's look at examples of complex numbers. So we have 3 minus 2i. So the 3 is the real portion, and the minus 2i, that's the imaginary portion. We also have 4i. So 4i, we can write that as 0 plus 4i, where 0 is the real portion and 4i is the imaginary portion. Take a look at 89. 89 is also a complex number. And you may be thinking, hang on, shouldn't it have an I? No. Remember, complex numbers are a combination of real numbers and imaginary numbers. Recall in the diagram on the first slide, we had complex numbers, and that incorporated the real numbers and the imaginary numbers. So 89 is a real number, hence it is also a complex number. Another easier way that I can show you that is 89 can be written as 89 plus 0i. And 0 times I, that's just going to be 0, so we get 89. So 89, that has 89 as the real portion and 0i as the imaginary portion. The same applies for minus 2. We also have 6 plus 7i, that's a complex number. We also have 4 minus root 7 over 2 multiplied by I, the imaginary unit. That's a complex number. So any number, what I'm trying to show you here is that any number that you're going to deal with in this lesson, it's going to be a complex number. Doesn't matter if it's real or if it's just imaginary or if it's a combination of both. They're all going to be complex numbers. Now let's move on to the Argand plane. And the Argand plane is actually nothing new. It's basically another Cartesian plane. So if you understand how stuff works in the Cartesian plane, the Argand plane is going to be extremely easy to understand. Another term that the Argand plane is called, it's called the complex plane because it's used to represent complex numbers. So let's go through this slide. Real numbers are represented on a real number line. Okay, basic stuff. You have the real number line. Here's 0. Then you have your, well, there's 0, and then you have your positive numbers and your negative numbers to the left of 0. So here's a cool picture that I found of the real number line. There's 0, you have 1, 2, 3, 4, 5, negative 1, 2, 3, 4, and then all the way to negative 5. You have some fractions, decimals, Euler's number, pi, those irrational numbers. Everything is on that real number line. Now a question arises. We can represent real numbers on this real number line. How are we going to represent complex numbers? Is there another number line for complex numbers? So that's where the Argand plane or the complex plane, as I've suggested, comes into play. A complex number, so we have z is equal to a plus bi, so we have this complex number z, can be represented by the ordered pair a and b. So the real portion is a, and that's going to be basically our x coordinate. You can think of it like that. And then we're going to have our imaginary portion, that's bi, but we're just going to look at the coefficient of I. So in this case, it's positive b. So that's why b is our second point in that ordered pair, that second number in the ordered pair. That's basically like a y component, or sorry, a y coordinate. Now this ordered pair can be plotted in a plane known as the Argand plane. And the Argand plane is basically a two-dimensional plane like the Cartesian plane, except that the axes represent real and imaginary numbers instead of x and y real numbers. So recall when we were dealing with the Cartesian plane. Here's the Cartesian plane. We had our x-axis and our y-axis. We had 1, 2, 3, 4. Those were all real numbers. And on the y-axis, we had 1, 2, 3, 4. Those were all real numbers. And we could represent an ordered pair in the Cartesian plane. Now all we're doing is the x-axis, we're leaving that as is. It's going to contain real numbers, right? But we're not going to call it the x-axis. We're going to call it the real number axis. Okay, basically the real number line. Then what we're doing, instead of the y-axis having real numbers on it, we're going to have imaginary numbers. So it's going to be positive I, positive 2I, then we'll have positive 3I, positive 4I, and so on. And below the real number axis, we're going to have negative I, negative 2I, negative 3I, and so on. We can also have fractional units of the imaginary units. So what I mean by that, we can have half I, we can have root 2 over 2I, we can have negative root 2 over 2I. That still applies. So the x-axis from the Cartesian plane to create the eigenplane basically becomes the real number axis, and the y-axis becomes, and I use the word becomes in inverted commas, it's because we're basically dealing with just a Cartesian plane at its core. Okay, nothing new has changed except now that we're working with complex numbers. So the y-axis becomes the imaginary number axis, and sometimes the imaginary units are omitted for simplicity, okay, because it's understood that the y-axis now is going to represent imaginary numbers. So again, the eigenplane or complex plane is really nothing new. All we're doing is we're taking an ordinary Cartesian plane and we are now going to represent an imaginary number a plus bi as an ordered pair in that plane, where we look at a and b. So the a is basically an x coordinate and the b is basically a y coordinate. Let's do an example and I'll show you how this is basically the same thing as the Cartesian plane. So exercise 1. I want you to plot the following complex numbers in an argand plane. Okay, so let's go for the first one. So the first one is -1 plus I. Let's draw our argand plane, basically a Cartesian plane. Now here we're going to have the real numbers. I'll represent that with RE. And here we're going to have the imaginary numbers. Okay, on my y-axis, that's going to be IM. So we have -1 plus 1I. So we represent that with the ordered pair of -1 and +1, because +1 is the coefficient of that I term. Okay, so -1 and +1, that is here, right? So that's going to be point A, okay, for that one. Next, we have, let's check 3 minus I. So our ordered pair is going to be 3, and be careful, our coefficient is not 1. Our coefficient is -1. Okay, basically it's 3 plus -1i. That's how you can write that out, 3 minus I. So we have to represent the ordered pair 3 and -1. Let's check, that's going to be 3 units here. So that would be somewhere there. Okay, so that's going to be B. Next we have 7i. So this is 0 plus 7i. We can represent that ordered pair 0, +7. So 0 on the real number line, and then we have 7 on the imaginary axis. That's going to be somewhere here. That's going to be point C. Then we're going to have 5. So 5, we can represent that as 5 plus 0i. And that's going to be the ordered pair 5, and the coefficient of I is 0. So that's going to be sitting on the real number line. That is going to be, let's check somewhere here. Okay, so that's going to be D. And then we have lastly I4, I to the power 4 plus 1. So let's just simplify that. Okay, because remember, on the argand plane, we can only represent it if it is in the form A plus BI. This is not in the form A plus BI. So we need to simplify it and get it into that form. Why isn't it in the form? Take a look at I is raised to the power 4. In this form, I is just raised to the power 1. Okay, so let's simplify it. I to the power 4, well, that's I squared, all squared plus 1. I squared squared, that gives us I to the power 4. Law of exponents, 2 times 2 is 4. We'll get I to the power 4. I squared we know is -1, and that's going to be squared plus 1. So we have -1 squared, that's just +1, plus 1, that's equal to 2. So this is actually just equal to 2. So it's 2 plus 0i, and that's represented by the ordered pair 2 and 0. So let's check where 2 and 0 would go. That would be here. Okay, about there. So that's going to be point E. All right, and that's how simple it is. That's how you represent complex numbers on the argand plane or the complex plane. All you have to do is ensure that the expression that you are given is in this form a plus bi. If it's not, you can simplify it like we did for the last question, get it into that form, and then just represent it as an ordered pair and plot it as if you were working with a Cartesian plane. Again, it's basically a Cartesian plane. We're just calling it something different, argand plane or complex plane.